Hello, friend. Welcome to a quiet corner of the universe where we drift softly through the mysteries that wait in the dark. Some nights the sky feels deeper than it should. Stars blink their ancient light across distances too vast to hold in your mind. And somewhere out there, hidden in the velvet black, there are places where time itself forgets how to move forward. Places where light, that restless traveler, finally stops running. Tonight, we're going to visit one of those places. A black hole. Not the monster you might imagine, but something stranger, quieter, more beautiful. A place where gravity learned to whisper secrets that even Einstein struggled to hear. Before we begin our journey, if you find comfort in these quiet explorations through the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. No pressure, just an invitation to drift together through the dark. Now, let's begin. Close your eyes for a moment and picture this. You're standing beneath a winter sky, breath turning to mist, looking up at the Milky Way. Every point of light you see is a star, and every star is a sun, some larger than ours, some smaller, each one burning through its fuel at its own patient pace. But here's something most people don't realize. Right now, as you stand there, you're also looking at ghosts. Some of those stars died thousands of years ago. Their light is still traveling toward you, a message sent from a sender who no longer exists. And when certain stars die, the very largest ones, they don't just fade away. They collapse into something so dense, so impossibly compressed, that they tear a hole in the fabric of space itself. That's not poetry, that's physics. Scientists call these objects black holes, though the name is misleading. They're not holes, not in the way you'd imagine. They're not empty. They're not tunnels to somewhere else. A black hole is a place where so much matter has been crushed into so small a space that gravity becomes overwhelming. Imagine taking our sun, which is about 865,000 miles across, and compressing it down until it fits inside a ball just 4 miles wide. Actually, don't just imagine it. Feel the weight of that thought. All that mass, all that matter squeezed until the atoms themselves give up and collapse. That's the birth of a black hole. But here's where it gets strange, beautifully strange. Near a black hole, time doesn't behave the way it does here on Earth. Clocks slow down, seconds stretch. If you could watch someone fall toward a black hole from a safe distance, you'd see them moving slower and slower, their image freezing at the edge, suspended forever in that final moment. To them, time would feel normal. They'd fall right through. But to you, watching from far away, they'd never quite reach the edge. They'd hang there caught in time's strange gradient, a photograph that never fades. Einstein predicted this in 1915 with his general theory of relativity, though even he found it unsettling. The mathematics were clear, precise, undeniable. Massive objects don't just pull on other objects, they bend the space around them. And when space bends, time bends with it. It's all one fabric space-time, curved and stretched by anything with mass. The sun creates a gentle dip in space-time, like a marble resting on a stretched sheet. Earth rolls along the curve of that dip, and we call it an orbit, but a black hole. A black hole doesn't create a dip. It creates a tear, a place where the fabric curves so sharply that it folds back on itself. The first person to realize this, to actually solve Einstein's equations and find black holes hiding in the mathematics, was a German physicist named Karl Schwarzschild. The year was 1916, and Schwarzschild was serving in the German army during World War I, calculating artillery trajectories by day. But at night in his tent by candlelight, he was working on something else entirely. He was exploring Einstein's new equations so complex that Einstein himself hadn't found all their solutions. And there in the middle of a war, Schwarzschild discovered something extraordinary. If you compressed enough mass into a small enough space, you'd create a boundary, a point of no return, where not even light could escape. He sent his calculations to Einstein, who was amazed and a little disturbed by what Schwarzschild had found. Schwarzschild died 4 months later from an illness contracted at the front. He never saw his work transform our understanding of the universe. But today, that boundary, that point of no return around a black hole, is called the Schwarzschild radius in his honor. For our sun, if it were somehow compressed into a black hole, that radius would be about 1.8 miles. For Earth, just over a third of an inch. A sphere smaller than a marble containing our entire planet's mass. Now, you might be thinking, if black holes are so powerful, so all-consuming, why isn't everything getting sucked into them? This is one of the most common misconceptions about black holes. They don't roam through space like cosmic vacuum cleaners, devouring everything in their path. Gravity follows rules, predictable rules. If our sun suddenly became a black hole, which it won't, it doesn't have enough mass. But if it did, Earth would continue orbiting exactly as it does now. The gravity at our current distance wouldn't change at all. Black holes only become dangerous if you get close, very close, within a few times that Schwarzschild radius. In fact, there's a supermassive black hole at the center of our galaxy right now, a giant with the mass of about 4 million suns. And we've named it Sagittarius A. It sits there 26,000 light-years away, anchoring the Milky Way, and we're perfectly safe. Stars orbit it in great slow loops. Some complete their orbits in just over a decade, moving at speeds that seem impossible, and astronomers have watched them, track them, use their motion to measure the black hole's mass with precision. One star called S2 gets so close to Sagittarius AOS that it experiences measurable time dilation. When it swings past the black hole at its closest approach, time for that star runs about 30 seconds slower per year compared to time here on Earth. 30 seconds. Not much perhaps, but enough to measure, enough to prove that Einstein was right. Let's stay with that idea for a moment. Time slowing down. It's not science fiction. It's not a metaphor. It's real, and we've measured it not just near black holes, but in much gentler circumstances. GPS satellites orbiting Earth experience this effect. They're farther from Earth's center than we are, so gravity is slightly weaker up there, and time for them runs just a tiny bit faster, about 45 microseconds per day, faster than time on the ground. That might not sound like much, but GPS relies on incredibly precise timing. If we didn't account for that time difference for that tiny shift caused by Earth's gravity, your GPS would be off by miles within a single day. Engineers have to program Einstein's equations into every GPS satellite. Relativity isn't abstract theory. It's the reason you can navigate to the grocery store. But near a black hole, the effect becomes dramatic. Imagine you had a twin, and one of you stayed on Earth while the other traveled to a black hole and hovered just outside the Schwarzschild radius for what felt like 1 year. When the traveling twin returned, they'd find that decades, maybe centuries, had passed on Earth. Their twin would be long gone. The Earth itself would have changed beyond recognition. This isn't a trick or a paradox. It's geometry. The traveling twin moved through space-time along a different path, a path where the geometry was curved more sharply. And when you travel along a sharply curved path through space-time, less time accumulates for you. Sometimes people ask, but what does time slowing down even mean? Isn't time just something we invented a way of measuring change? That's a beautiful question, and the answer is both yes and no. Time as a concept measured in hours and minutes is a human invention. But time as a dimension is something that can be stretched and compressed, is woven into the structure of reality itself. Think of it this way. Distance is real, even though we invented miles and meters. You can walk from here to there, and the space you cross is actual measurable part of the universe. Time works the same way. It's a dimension you move through, and gravity affects how you move through it. There's something almost poetic about that. The universe doesn't care about our clocks, our schedules, our impatience. Time flows at its own pace, determined by the shape of the space you're in, by the mass nearby, by the curve of reality beneath your feet. Near a black hole, Reality curves so sharply that time nearly stops, and light, which always moves at the same speed through space, finds that the space itself has become a trap. Which brings us to something crucial, something that will matter as we drift deeper into this story. Light doesn't slow down near a black hole. Light always travels at exactly the same speed, about 186, 282 miles per second, no matter where it is or what's happening around it. But space itself can curve, can stretch, can flow. And if space is flowing inward toward a black hole faster than light can escape outward, then light gets trapped. It's still moving at light speed, still doing everything it's supposed to do, but the space it's moving through is pulling it backward. Imagine running up a down escalator that's moving faster than you can run. You're moving forward, your legs are pumping, but you're sliding backward anyway. That's light at the event horizon of a black hole, the event horizon. That phrase appears in almost every conversation about black holes, and it's worth understanding what it really means. It's not a surface, not a physical barrier. You couldn't touch it. You couldn't see it if you were falling toward it. It's simply a boundary, a mathematical line in space beyond which escape becomes impossible. Cross that line, and every direction you could move, every path you could take leads inward. There is no outward anymore. The geometry of space-time itself has conspired to eliminate the very concept of away from the black hole. Scientists sometimes compare it to a waterfall. Imagine you're in a canoe paddling upstream. As long as you're far from the waterfall, you can make progress. You can move up or down the river as you choose. But as you get closer, the current gets stronger. Eventually, you reach a point where the water is flowing toward the falls faster than you can paddle. You're still paddling, still trying, but you're being swept backward. That point where the current equals your maximum speed is like the event horizon. Beyond it, no amount of effort will save you. You're going over. Except with a black hole, it's not water flowing. It's space itself. People have asked whether we've ever actually seen a black hole. The answer is complicated. By definition, a black hole emits no light, so you can't see one directly. But you can see its effects the way matter swirls around it, heating up, glowing, screaming with X-rays as it's torn apart just before falling in. And in 2019, scientists released the first direct image of a black hole's shadow, the silhouette of the event horizon against the bright disk of matter surrounding it. The black hole was M87C sitting at the center of a galaxy, 55 million light-years away. And it was enormous, with a mass of 6.5 billion times our sun. The image showed a dark circle surrounded by a glowing ring, and when it was published, people around the world stopped and stared. For the first time, we weren't imagining. We were seeing. The darkness was real. That image took years to create. Astronomers combined data from radio telescopes scattered across the entire Earth, effectively building a telescope the size of our planet. They gathered petabytes of data, so much information that it had to be physically shipped on hard drives because it was faster than sending it over the internet. And then they processed it, filtered it, aligned it until finally the image emerged. A ring of light around a sphere of dark, simple, profound. Proof that Einstein's strange predictions were not just mathematics, but reflections of reality. What does it feel like knowing that such places exist? Not in stories, not in theory, but out there in the actual universe right now. Black holes don't care whether we believe in them. They don't wait for us to understand. They simply are patient and silent, bending time and light and space into shapes we're still learning to comprehend. And here's the strangest part of all. Every black hole was once a star. Every single one. They were born from collapse, from the death of something that once shone brightly. Something that spent millions or billions of years burning fuel, creating light-warming planets that might have orbited nearby. And when the fuel ran out, when there was nothing left to push back against gravity's inward pull, the core collapsed. And in that collapse, if the star was massive enough, it created a black hole. Death and transformation, ending and beginning all at once. We'll explore that transformation soon, the way stars choose their endings, why some fade gently while others collapse into eternal darkness. We'll walk through the mathematics that predict these objects, the strange history of their discovery, the debates and doubts that once surrounded them. We'll talk about what happens at the edge of a black hole, that strange frozen boundary where time dilates toward infinity, and what might lie beyond at the center where our physics breaks down and the universe refuses to show us what comes next. But for now, rest in this thought. Somewhere out there, not far by cosmic standards, there are places where time slows to a whisper, where gravity bends reality into shapes we can barely imagine, where light itself gives up the fight and falls forever inward. And we, from our small blue world spinning quietly in the suburbs of the Milky Way, have learned to see them, measure them, understand them at least a little. It's one of the most extraordinary things our species has ever done. Looking up at the night sky and finding hidden in the mathematics of curved space-time, the places where the universe keeps its deepest secrets. The story of black holes is not just a story of darkness. It's a story of light of the stars that came before, of the violent beauty of their endings. And that's where we'll turn next to the moment when a star burning bright and steady for billions of years finally runs out of time and makes its choice, to fade or to fall, to drift away or to collapse into something stranger than night itself. Every star is born with a death already written into its atoms. The fuel it burns, the light it gives, the warmth it radiates across billions of miles, all of it is temporary borrowed time against the patient pull of gravity. And when that time runs out, when the last of the hydrogen fuses into helium, when the core cools and the outward pressure fades, gravity wins. But how it wins, how the star falls, depends entirely on how massive it was to begin with. Not all stars die the same way. Some go quietly, others explode, and a rare few collapse so completely that they vanish from the universe as we know it, leaving behind only gravity's ghost. Let's start with something familiar, our sun. It's been burning for about 4.6 billion years, fusing hydrogen into helium in its core, releasing energy that takes tens of thousands of years to fight its way from the center to the surface, and then just 8 minutes to cross the space between the sun and Earth. That energy is what keeps you warm, what makes plants grow, what drives weather and ocean currents and every living thing on this planet. But the sun won't burn forever. In about 5 billion years, it will begin to run low on hydrogen fuel in its core. The fusion will slow, the core will contract, and as it contracts, it will heat up, which seems backward, doesn't it? You'd think cooling down would make things colder, but gravity is compressing the core, squeezing it tighter, and compression generates heat. That heat will reignite fusion in a shell around the core, and the sun will swell, expanding outward into a red giant. It will grow so large that it will likely swallow Mercury, possibly, Venus, maybe even Earth, though by then, Earth will already be a scorched, lifeless rock. The sun will burn helium into carbon and oxygen, and when that fuel runs out, it won't have enough mass to ignite anything heavier. The core will collapse one final time, squeezing down into something called a white dwarf, a sphere about the size of Earth, but with half the sun's mass packed inside. And there it will sit, cooling slowly, radiating the last of its heat into the void, taking trillions of years to fade into a cold, dark cinder. That's the fate of stars, like our sun stars, with masses between about 1/2 and 8 times the sun's weight. They die with a sigh, not a scream. But larger stars, stars with 10, 20, 50, 100 times the sun's mass, they have a different ending, waiting. These giants burn hotter, faster, fiercer. They race through their fuel in just a few million years instead of billions. They fuse hydrogen into helium, helium into carbon, into oxygen, into neon, into magnesium, silicon, into iron, building heavier and heavier elements in layers like an onion. And here's where the story changes. Iron is different. Every element lighter than iron releases energy when it fuses. That energy pushes outward, holding the star up against gravity. But iron absorbs energy when it fuses. It takes more energy to fuse iron than you get back. So, when the core of a massive star turns to iron, fusion stops. Just stops. And there's nothing left to push back. What happens next occurs in less than a second. The core, which has been held up by the pressure of fusion for millions of years, collapses. Not gradually, not slowly. It falls inward at nearly a quarter the speed of light. In 1 second, a core the size of Earth compresses down to a sphere about 12 miles across. The density becomes unimaginable. A teaspoon of that material would weigh as much as Mount Everest. Protons and electrons are squeezed together so tightly that they merge into neutrons, and the core becomes a solid ball of neutron matter, the densest stable form of matter in the universe. The outer layers of the star, suddenly finding nothing beneath them to rest on, fall inward too. They hit the neutron core and bounce. That bounce sends a shockwave ripping back outward through the collapsing star, and the star explodes. A supernova. For a few weeks, that single dying star will shine as brightly as an entire galaxy, outshining hundreds of billions of stars combined. The explosion flings the outer layers into space at thousands of miles per second, scattering the elements the star spent its life creating. Carbon, oxygen, nitrogen, calcium, iron, gold, uranium. All the heavy elements that make up planets and people forged in the furnace of a dying star and hurled into the cosmos. In 10 of 54, Chinese astronomers recorded a new star appearing in the constellation Taurus, bright enough to see in daylight for weeks. They called it a guest star. We now know it was a supernova, and the expanding cloud of debris from that explosion is called the Crab Nebula. It's still expanding today, still glowing, a monument to a star that died nearly 1,000 years ago. But here's the critical question. What's left behind after the explosion? What happens to that neutron core? If the original star was between about 8 and 20 times the sun's mass, the core survives as a neutron star, spinning wildly, sometimes hundreds of times per second, blasting beams of radiation into space like a cosmic lighthouse. We call them pulsars when those beams sweep past Earth, and we can detect their rhythmic pulses with radio telescopes. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge. She noticed a repeating signal in her data, pulsing every 1.33 seconds, so regular and precise that her team briefly wondered if it might be an alien transmission. They even jokingly called it LGM-1 for little green men. But it wasn't aliens. It was a neutron star, the collapsed core of a dead sun, spinning and radiating and refusing to fade quietly. Neutron stars are strange beyond description. A sugar cube of neutron star material would weigh about 1 billion tons. The gravity at the surface is so intense that if you could somehow stand on one, you'd be flattened to less than 1 millimeter thick in an instant. The magnetic fields are the strongest in the known universe, trillions of times stronger than Earth's, and they spin so fast that their surfaces move at a significant fraction of the speed of light. They're not quiet, they're not peaceful. They're violent remnant scars left by stars that died screaming. But if the star was even more massive, if the core left behind weighs more than about 3 times the sun's mass, then even neutron matter can't hold it up. There's a limit calculated by physicists J. Robert Oppenheimer and Hartland Snyder in 1939 called the Tolman-Oppenheimer-Volkoff limit. Beyond that mass, no known force in physics can prevent collapse. The neutrons themselves give up. The core compresses past the neutron star stage, past any stable configuration, and it keeps falling inward. The escape velocity at the surface exceeds the speed of light. An event horizon forms. And what's left is no longer a star. It's a black hole. Think about that for a moment. A star that once filled a volume larger than Earth's orbit around the sun, a star that burned for millions of years, collapses down into a point so small that it has no physical size at all. only mass and gravity, and the warped space-time around it. Everything that star was all its light, all its energy, all the nuclear reactions that powered it, compressed into a singularity, a place where the mathematics of physics break down. And we have to admit, we don't know what happens next. It's worth pausing here to compare the different fates of stars, because mass makes all the difference. A star like our sun will end as a white dwarf, cooling for trillions of years. A star 10 times the sun's mass will explode and leave behind a neutron star, dense and spinning and strange. A star 30 times the sun's mass will explode even more violently and leave behind a black hole, a gravitational trap from which not even light escapes. Same basic process, fusion and collapse, but the endings couldn't be more different. And here's something people often get wrong. They imagine black holes forming slowly, gradually, like sand piling up in an hourglass. But the collapse happens fast, catastrophically fast. From the moment the iron core can no longer support itself, the formation of a black hole takes less than a second. One moment there's a star, the next there's an explosion. And in the heart of that explosion, where the core used to be space-time itself, is tearing open. Astronomers have observed this process indirectly many times. When a massive star explodes as a supernova, we can measure the light curve, the way the brightness rises and falls over days and weeks. We can analyze the spectrum, identifying the elements being flung into space. And sometimes, when we look at the center of the remnant years later, we find nothing. No neutron star, no pulsar, just empty space where the core should be. That absence is the signature. The core collapsed completely. A black hole was born. One of the most famous examples is SN 1987A, a supernova that exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, visible from the southern hemisphere. When it detonated in February 1987, it was the brightest supernova seen from Earth in nearly 400 years. Astronomers around the world trained their telescopes on it, studying every detail. They detected neutrinos from the collapsed ghostly particles that barely interact with matter streaming out from the dying core. Those neutrinos arrived at Earth about 3 hours before the visible light. Because they escaped from the core immediately, while the light had to fight its way through the star's outer layers. It was a triumph of astrophysics. Theory predicted neutrinos. Observation confirmed them. But here's the mystery. When astronomers looked for the remnant expecting to find a neutron star or pulsar at the center, they found nothing conclusive. The remnant is obscured by dust and debris, still expanding, still glowing. Some scientists suspect a black hole formed. Others think a neutron star is hiding in there, somewhere too faint to detect yet. We're still waiting, watching, letting the debris clear, hoping that in another decade or two, we'll finally see what was left behind. That's the nature of studying black holes from stellar collapse. We see the explosion, we measure the mass, we calculate whether the core was heavy enough to overcome neutron degeneracy pressure. But we can't watch the black hole form directly. It happens in an instant, hidden inside a fireball brighter than 1 billion suns. By the time the light reaches us, the deed is done. There's something almost poetic about that. Don't you think stars spend millions of years burning, shining, radiating light across the universe? And then, in the final second, they make a choice they can't take back. Collapse or hold. Neutron star or black hole. A line in the mathematics drawn by mass that separates two completely different destinies. And it's worth noting that the transition isn't clean. There's a gray zone, a mass range, where we're not entirely sure what happens. If a core is right at the edge, around 2.5 to 3 solar masses, does it form a neutron star that later collapses? Does it form a black hole immediately? Does something else happen, something we haven't thought of yet? These are open questions. The universe doesn't hand us easy answers. It makes us work for them. Observe, measure, test our theories against reality until the picture becomes clear. Consider for a moment the difference in outcomes. A white dwarf is stable. It will sit there cooling for longer than the current age of the universe. A neutron star is stable to spinning and radiating, but fundamentally unchanging. But a black hole. A black hole has no internal structure to speak of. No layers, no composition, no material holding it up. Just gravity folding space-time into a shape so extreme that the normal rules of cause and effect start to blur. And here's the thing that keeps physicists awake at night. We don't know what's at the center. The mathematics of general relativity predict a singularity, a point of infinite density, but infinity is almost always a sign that the theory is breaking down, that we're missing something. Maybe quantum mechanics steps in at the smallest scales. Maybe space-time itself becomes grainy, pixelated, discrete. Maybe there's a whole new layer of physics waiting to be discovered, hidden inside black holes, where we can't see it. But we're getting ahead of ourselves. Before we dive into singularities and quantum mysteries, we need to understand the boundary, the place where the black hole announces itself to the universe. The event horizon, that strange invisible edge where the rules change, where time dilates toward infinity, where infall becomes inevitable. We've talked about how black holes form the violent collapse of massive stellar cores. We've seen that they're not rare, not mythical, but the natural endpoint of stars that were simply born too large. Now, we need to understand what they are, how they shape the space around them, and why crossing that boundary, that edge of forever, is a one-way journey into the unknown. Imagine standing at the top of a mountain right at the peak where the land falls away in every direction. There's a line up there, invisible but real, where rainwater makes a choice. A drop that falls on one side flows west toward the Pacific. A drop that falls on the other side flows east toward the Atlantic. The line itself, the continental divide, is just geometry, just the shape of the land. But it determines everything that happens to that water afterward. Once a raindrop crosses that line, its fate is sealed. The event horizon of a black hole works the same way, except instead of water flowing downhill, it's space-time itself that's flowing, carrying everything with it, light included. And the horizon isn't a ridge you can stand on. It's a boundary you can cross without even noticing, until you try to turn back and realize there is no back anymore. Let's talk about what an event horizon actually is, because the name itself is beautiful and precise. An event is something that happens a point in space-time. The horizon is the limit of what you can see. Put them together, and you get the event horizon, the boundary beyond which events cannot be seen by the outside universe. Cross that line, and nothing you do, no signal you send, no light you shine, will ever reach anyone outside. You've passed beyond the edge of forever. Here's the strange part. The event horizon isn't made of anything. It's not a surface. There are no atoms there, no particles, no fabric stretched across space. It's purely geometric, a consequence of how severely space-time is curved near a massive object. If you were falling toward a black hole, you wouldn't feel anything special as you crossed the horizon. No bump, no barrier, no sudden change. You'd sail right through, probably not even realizing the moment had passed. But from that instant forward, every direction you could move, every possible future path, would lead deeper inward. The size of the event horizon depends on the black hole's mass, and there's a simple relationship discovered by Carl Schwarzschild. The radius of the horizon, called the Schwarzschild radius, is equal to 2 times the gravitational constant times the mass divided by the speed of light squared. Don't worry about memorizing the equation. What matters is the radius grows directly with mass. Double the mass, double the radius. A black hole with 10 times the sun's mass has a Schwarzschild radius of about 18.5 miles. A black hole with 1 million solar masses has a radius of about 1.8 million miles, roughly twice the distance from Earth to the sun. Let's put that in perspective with something tangible. If you could somehow compress Earth, all 5.97 trillion kilograms of it, down into a black hole, the event horizon would be a sphere about 0.35 inches across, smaller than a marble. All the mountains and oceans and cities and people, the entire mass of the planet hidden inside a space you could hold between your thumb and finger. The moon compressed the same way would have an event horizon about 1/10 of a millimeter, wide, smaller than a grain of sand. And the sun, our massive brilliant sun, would fit inside a sphere less than 4 miles across. Those numbers feel impossible, don't they? But they're real, calculated from equations that have been tested and verified in countless experiments. The universe doesn't care about our intuition. It follows rules, mathematical rules. And those rules allow for objects so dense that they warp space-time beyond recognition. Now, here's a mistake people often make. They think of black holes as cosmic vacuum cleaners roaming through space and sucking up everything around them. But gravity doesn't work that way. Gravity follows an inverse square law, meaning its strength decreases with the square of the distance. If the sun suddenly turned into a black hole, which it won't, because it lacks the mass, but if it did, Earth would continue orbiting exactly as before. The gravitational pull at our current distance, 93 million miles away, would be identical. We'd lose the sunlight. We'd freeze. The planet would become a lifeless ice ball. But we wouldn't spiral into the black hole. Gravity doesn't change just because the object is denser. Black holes only become dangerous when you get close, very close, within a few times the Schwarzschild radius. Out beyond that, they're just massive objects, no more threatening than any star of the same mass. In fact, there are binary systems where a normal star orbits a black hole, and they've been doing so for millions of years without the star getting devoured. The black hole only feeds when matter drifts too close, usually from the outer layers of the companion star being pulled away by tidal forces. One such system is Cygnus X1, discovered in 1964 as a powerful source of X-rays in the constellation Cygnus. For years, astronomers debated what it was. The X-rays suggested something hot, something energetic, but there was no visible star at that location. Eventually, they realized the X-rays were coming from gas, spiraling into a black hole, heating up to millions of degrees as it fell. The black hole itself has a mass of about 15 times the sun, and it's orbiting a blue supergiant star, slowly stripping away the star's outer layers. It's been doing this for thousands of years, maybe longer, and it will continue until the star finally exhausts itself. Stephen Hawking, the brilliant physicist who spent much of his career studying black holes, once made a famous bet about Cygnus X1. In 1974, he bet fellow physicist Kip Thorne that Cygnus X1 did not contain a black hole. Hawking later said he made the bet as a form of insurance. If black holes didn't exist, at least he'd win a subscription to a magazine. But as evidence mounted over the years, observations became more precise, calculations more certain. Hawking conceded the bet in 1990. Cygnus X1 was indeed a black hole. Thorne received his prize, a one-year subscription to a particular magazine, and Hawking's concession was written into the pages of scientific history. Let's return to the event horizon itself, because there's something deeply strange about how it behaves depending on where you're watching from. Imagine you're safely far away watching a friend fall toward a black hole. As your friend gets closer to the horizon, you notice them slowing down, not because they're trying to stop, but because time itself is running slower for them relative to you. The light from their spacesuit would shift toward the red end of the spectrum, growing dimmer and dimmer. Eventually, they would appear to freeze locked at the horizon, their image fading, but never quite disappearing. From your perspective, they never cross. They hang there forever, stretched and frozen at the edge. But from your friend's perspective, everything feels normal. Time passes normally. They don't slow down. They don't freeze. They fall right through the horizon in a finite amount of time, maybe a few seconds, maybe a fraction of a second, depending on the black hole's size. They wouldn't even know the exact moment they crossed. The horizon is only special to someone watching from outside. To someone falling through, it's just another point in space. This creates a paradox that physicists have wrestled with for decades. If you watch someone fall into a black hole, you never see them cross the horizon. They're stuck there forever from your point of view. But from their point of view, they crossed and continued falling. So, which is real? Did they cross or didn't they? The answer is both. It depends on your reference frame, your perspective in space-time. This is one of the core insights of relativity. There's no absolute truth about the order or timing of events separated by large distances or strong gravitational fields. Two observers can disagree about what happened when, and both can be right. Your friend crossed the horizon from their own perspective. They never crossed from yours. Both statements are true simultaneously because time and space aren't fixed universal stages. They're woven together into a fabric that bends and stretches depending on where you are and how you're moving. Let's think about this with a different analogy. Imagine you're watching a river flow toward a waterfall. You place a toy boat in the current far upstream. At first, the boat drifts slowly, but as it approaches the falls, the current speeds up. From your position on the shore, you see the boat accelerate, tipping over the edge and disappearing. But if you were in the boat small enough to ride it, you'd feel the acceleration as a smooth increase in speed, and you'd go over the falls without any sense that you'd cross some special boundary. The edge of the waterfall is only significant from outside. From inside the boat, it's just the next moment. The event horizon is that edge, except instead of water, it's space-time that's flowing. And instead of falling over into a pool below, you're falling into a region where the future always points inward toward the singularity at the center. Scientists have calculated exactly what the Schwarzschild radius is for different masses, and the results are fascinating. For a black hole with the mass of our Sun, the radius is about 1.9 miles. For a black hole with 10 solar masses, it's about 19 miles. For the supermassive black hole at the center of our galaxy, Sagittarius A/Su, which weighs about 4 million times the Sun, the Schwarzschild radius is roughly 7.5 million miles, which sounds enormous until you realize that's only about 17 times the radius of the Sun. Pack 4 million suns worth of mass into a space 17 times wider than one sun, and you get a black hole. But here's something even stranger. The density inside the event horizon, the average density if you spread the mass evenly throughout the volume, actually decreases as the black hole gets bigger. A stellar mass black hole has an incredibly high average density, higher than any neutron star. But a supermassive black hole, despite having millions or billions of times more mass, has an average density that can be lower than water. That seems impossible, doesn't it? A black hole less dense than water. The key word there is average. All the mass is still concentrated at the singularity in the center, but the event horizon is so far away that the average density inside that volume is relatively low. It's a quirk of geometry, a reminder that black holes aren't about density alone. They're about compactness, about squeezing enough mass into a small enough space that escape velocity exceeds the speed of light. There's a thought experiment that helps clarify this. Imagine you could gather all the matter in the observable universe, every star, every planet, every speck of dust, and compress it into a black hole. The event horizon of that black hole would be about 13 billion light-years across, roughly the size of the observable universe itself. And the average density inside would be about the same as the average density of the universe right now, which is incredibly low, just a few hydrogen atoms per cubic meter. The entire universe, from a certain mathematical perspective, is close to being inside its own event horizon. That doesn't mean we live inside a black hole, but it does mean the geometry of space-time on cosmic scales is stranger and more subtle than we usually imagine. Let's talk about what happens at the horizon in terms of physics. One way to think about it is through the concept of escape velocity. On Earth, escape velocity is about 7 miles per second. Throw a ball upward slower than that, and it falls back down. Throw it faster, and it escapes into space. The Moon has a lower escape velocity because it's less massive. Jupiter has a higher one. The Sun's escape velocity at its surface is about 383 miles per second. Now, imagine compressing the Sun smaller and smaller. As the radius shrinks, the escape velocity at the surface increases. Eventually, when the radius reaches about 1.9 miles, the Schwarzschild radius, the escape velocity hits 282 miles per second. The speed of light. At that point, even light can't escape. The boundary where this happens is the event horizon. But here's the important part. Light doesn't slow down. Light always travels at the same speed in a vacuum no matter what. So, how can light be trapped? The answer is that space itself is falling inward faster than light can swim outward. It's like that down escalator again, moving faster than you can run. You're running at full speed, but you're still being carried backward. Light at the event horizon is doing the same thing, traveling at light speed outward, but being dragged inward by the flow of space-time. This is one of the hardest things to wrap your mind around, and even professional physicists sometimes struggle with the implications. Space isn't a static stage. It's dynamic, flowing, bending, twisting. Near a black hole, it flows inward like a river rushing toward a drain. Far away, the flow is gentle, barely noticeable. But close to the horizon, the flow accelerates until it becomes a torrent. And once you cross that boundary, the flow is so strong that all your possible futures, all the paths you could take through space-time, point inward. You can fire your rockets, you can shine a flashlight, you can scream and struggle, but it won't matter. The geometry of space-time itself has conspired to eliminate the direction called outward. It's not part of the map anymore. Think about how profoundly strange that is. Direction isn't just a choice, it's a feature of geometry. On Earth, you can always choose to go north, south, east, or west. You have freedom. But inside an event horizon, moving away from the singularity isn't an option. It's not forbidden by a law or a force. It's forbidden by the shape of reality itself. This leads to a question people often ask: what would you see if you were falling in? The answer depends on which direction you look. If you look outward away from the black hole, you'd see the rest of the universe compressed into a shrinking circle of light behind you, blue shifted and accelerating. Time out there would appear to speed up from your perspective. You might see stars born and dying in fast-forward galaxies, evolving the universe, aging in moments. If you look inward toward the singularity, you'd see darkness, the absence of light that's already fallen ahead of you. But here's the catch. You wouldn't have long to observe any of this. And that's where we need to turn next, to the forces that tear you apart as you fall to the gradient of gravity that stretches and compresses to the process with the oddly whimsical name that describes one of the most violent deaths imaginable: spaghettification. The point of no return isn't just a metaphor, it's a warning. Picture a trampoline stretched tight, its surface flat and smooth. Now, place a bowling ball in the center. The fabric sags, curves, forms a depression. Roll a marble near the edge, and it doesn't travel in a straight line anymore. It curves inward, spiraling around the bowling ball, following the shape of the bent surface. That marble isn't being pulled by some invisible string. It's simply moving along the straightest path it can find on a curved surface. This simple image, this backyard demonstration, captures one of the most revolutionary ideas in the history of physics. Gravity isn't a force reaching across empty space to pull objects together. Gravity is the shape of space itself, bent and curved by the presence of mass. And the person who figured this out, who saw through centuries of assumption to the deeper truth beneath, was Albert Einstein. In 1915, Einstein published his general theory of relativity, a set of equations so elegant and powerful that they transformed our understanding of the universe. Before Einstein, physicists used Isaac Newton's law of universal gravitation, which worked beautifully for most purposes. It predicted planetary orbits, explained tides, let engineers calculate trajectories. But Newton himself admitted he didn't know what gravity actually was. He could describe how it behaved, how it diminished with distance, but he couldn't explain why masses attracted each other. He famously said he would not feign hypotheses about the cause. The equations worked. That was enough. Einstein wasn't satisfied with that. He wanted to know why. And what he discovered was that gravity wasn't a force at all. It was geometry. Mass tells space-time how to curve, and curved space-time tells mass how to move. Those two sentences contain the essence of general relativity, though the full theory requires mathematics far beyond what most people encounter in their lives. Tensor calculus differential geometry equations that fill pages. But the core idea, the heart of it, is almost poetic. The universe is a fabric flexible and smooth, and matter shapes it. Let's walk through how this works gently without the mathematics. Imagine space-time as a four-dimensional fabric, 3 dimensions of space and 1 of time, all woven together. Normally, without any mass around, that fabric is flat, or as close to flat as makes no difference. Objects moving through it travel in straight lines at constant speeds unless something interferes. But when you place a mass in the fabric, it sinks, creating a curve, a dimple, a well. The more massive the object, the deeper the well. And anything moving nearby follows the curves of that well. Earth orbits the sun, not because the sun is pulling it with some mysterious force, but because the sun's mass curves space-time, and Earth is simply moving along the straightest path it can find in that curved geometry. We call those paths geodesics, the equivalent of straight lines on a curved surface. If you've ever flown from New York to London, you know the plane doesn't travel in a straight line on a flat map. It follows a curved path, a great circle route, because that's the shortest distance on the curved surface of Earth. Planets do the same thing in curved space-time. Einstein spent nearly a decade developing this theory, working through false starts, mathematical dead ends, moments of despair, and flashes of insight. He later described November 1915 as the most intense period of his life, racing to finalize the equations, checking and rechecking, driven by both excitement and fear that someone else might solve it first. When he finally arrived at the correct field equations, he tested them against a known problem. The orbit of Mercury, the innermost planet, had a peculiarity that Newtonian gravity couldn't fully explain. Mercury's orbit precesses, meaning the point of its closest approach to the Sun, slowly rotates over time. Newton's equations predicted most of that precession, but not all of it. There was a tiny discrepancy, just 43 arcseconds per century, a sliver of a degree, but it was real and measurable. Einstein plugged Mercury's orbit into his new equations, and they worked perfectly. The theory predicted the exact amount of precession that had been observed. Einstein later said that when he saw the result, his heart skipped a beat and he felt as if something had snapped inside him. This wasn't just mathematics. This was truth reflected in the motion of a distant world. But the real test came in 1919. Einstein's theory predicted that light, despite having no mass, should still be affected by gravity, because light travels through space-time, and space-time itself is curved. During a total solar eclipse, stars near the sun's edge should appear slightly displaced from their normal positions, because the sun's gravity bends the light from those stars as it passes by. The amount of bending was tiny, less than 2 arcseconds, but it was measurable. Arthur Eddington, a British astronomer, led an expedition to the island of Principe off the coast of West Africa to observe the eclipse and test Einstein's prediction. The timing was remarkable. World War I had just ended. Einstein was German. Eddington was British. And yet, here was science transcending borders, seeking truth regardless of nationality. Eddington photographed the stars during the eclipse, compared their positions to photographs taken at night when the sun wasn't there, and found the displacement Einstein had predicted. The announcement made headlines around the world. Newton overthrown. Einstein's theory triumphs. Overnight, Einstein became the most famous scientist on Earth. But let's return to the fabric, to what happens when you curve space-time, not just a little, but severely. When you place a truly massive object or compress a modest mass into a very small space, the curve becomes steep, dramatic, eventually so extreme that it folds back on itself. That's a black hole. Not a hole in the fabric, but a place where the fabric curves infinitely steeply, creating a pit with no bottom, a well with no escape. 4 months after Einstein published his equations, while World War I still raged across Europe, a German physicist named Karl Schwarzschild was serving on the Russian front, calculating artillery trajectories during the day. At night in his tent, he was working on Einstein's field equations. The equations were notoriously difficult to solve. Einstein himself had only found approximate solutions for special cases, but Schwarzschild, using mathematical techniques that remain impressive even today, found an exact solution for the space-time around a spherical, non-rotating mass. That solution described what we now call a Schwarzschild black hole. It showed that if you compressed any amount of mass inside a certain critical radius, the radius we've been calling the Schwarzschild radius, the geometry of space-time, would become so warped that not even light could escape. Schwarzschild sent his results to Einstein, who was both amazed and troubled. The mathematics were clear, but the implications seemed absurd. A region of space from which nothing could escape, a boundary beyond which time itself behaved strangely. It didn't seem physical. It seemed like a mathematical curiosity, an artifact of the equations, not something that could actually exist. Schwarzschild never saw his work vindicated. He contracted an autoimmune disease, pemphigus, while at the front and died just 4 months after publishing his solution. He was 42 years old. His name ironically means black shield in German, a coincidence that feels almost too perfect. Today, every non-rotating black hole is described by the Schwarzschild solution. His equations derived in a trench during wartime are the foundation of our understanding. For decades after Schwarzschild's death, physicists debated whether black holes were real or merely mathematical oddities. Einstein himself remained skeptical. In 1939, he published a paper arguing that black holes couldn't form in nature because matter would never collapse completely. Other physicists disagreed. J. Robert Oppenheimer, who would later lead the Manhattan Project, worked with his student Hartland Snyder to show that a sufficiently massive star could indeed collapse into a black hole. Their paper, published in 1939, described the process in detail, predicting the formation of what they called a frozen star. Frozen because time dilation would make the final collapse appear to take forever from an outside observer's perspective. But observational evidence was lacking. No one had seen a black hole. No one was even sure how you could see something that emitted no light. The idea remained theoretical, a prediction on paper waiting for technology to catch up. Let's talk about geodesics again, those paths through curved space-time. On flat space-time, a geodesic is just a straight line. You travel from point A to point B in a straight path at constant speed. But near a massive object, space-time curves and the geodesics curve with it. If you're in orbit around Earth, you're not fighting to stay up. You're not being held by some force. You're falling freely following a geodesic, and that geodesic happens to be a closed loop around the planet. Astronauts on the International Space Station aren't weightless because there's no gravity up there. Gravity at that altitude is only about 10% weaker than on the surface. They're weightless because they're in free fall following the curve of space-time, and so is the station beneath them. Now imagine the curve getting steeper. Near a neutron star, geodesics bend sharply. Near a black hole, they spiral inward. And at the event horizon, they curve so much that all future geodesics point toward the singularity. There's no path, no trajectory, no choice of direction that leads outward. The geometry itself has removed that option. This is the true meaning of escape is impossible. It's not that you lack the energy. It's not that you're not strong enough. It's that the space-time you're in doesn't have an outward direction anymore. Asking how to escape a black hole from inside the event horizon is like asking which direction is north of the North Pole. The question doesn't make sense. The geometry doesn't allow it. Einstein's equations also predict something strange about time near massive objects. Clocks run slower in stronger gravitational fields. This isn't just theory. It's been measured with atomic clocks on airplanes compared to identical clocks on the ground. The airborne clocks farther from Earth's center and in slightly weaker gravity run faster. The difference is tiny nanoseconds, but it's real and measurable. GPS satellites experience the same effect. They're in weaker gravity than we are on the surface, so their clocks run faster, and the system has to account for that difference, or navigation would fail. Near a black hole, the effect becomes extreme. Imagine two clocks, one held by an observer far from the black hole, one dropped toward the event horizon. As the falling clock approaches the horizon, it ticks slower and slower from the distant observer's perspective. Not because the clock is broken, but because time itself is running slower. If you could watch the falling clock with a powerful telescope, you'd see its hands move more and more, slowly approaching, but never quite reaching a final moment. The clock is experiencing less time than you are over the same interval. This leads to one of the strangest predictions of general relativity. If you could survive falling into a black hole, and you looked back at the universe outside, you'd see it aging and fast forward. Stars would be born and die in moments. Galaxies would collide and merge. The universe would evolve before your eyes compressed into the brief seconds of your fall. Meanwhile, anyone watching you would see you slow down, freeze, fade, locked forever at the edge. Both perspectives are valid. Both are true. Time is not absolute. It depends on where you are and how space-time is curved around you. Let's consider a practical example to ground this. Imagine a spaceship hovering just outside the event horizon of a black hole with 10 solar masses. The ship's engines are firing constantly, fighting to stay in place against the inward flow of space-time. An astronaut on that ship decides to drop a probe into the black hole and watch what happens. The probe is equipped with a clock and a transmitter. As it falls, the astronaut watches through a telescope. At first, the probe falls quickly, accelerating. But as it nears the horizon, it appears to slow down. The clock on the probe ticks slower and slower. The light from the probe shifts toward the red dimming. The probe's image stretches, distorts, and finally fades into invisibility as it reaches the horizon. From the astronaut's perspective, the probe never quite crosses. It hangs there frozen. But if you were riding on the probe, you'd experience something completely different. The clock would tick normally. You'd accelerate smoothly. And in perhaps a fraction of a second, you'd cross the horizon feeling nothing unusual at the moment of crossing. You'd continue falling the singularity ahead, the universe behind. And you'd wonder why anyone thought this boundary was special. Einstein spent years trying to reconcile these perspectives, trying to understand what it meant for time to behave so differently depending on where you stood. He never fully accepted black holes as real objects, even though his own equations predicted them. It's a reminder that even the greatest minds struggle with the implications of their discoveries. The fabric of space-time, as Einstein imagined it, is flexible but never breaks. It curves, stretches, bends under the weight of mass and energy. Near a black hole, it curves so sharply that the geometry itself becomes a trap. But it doesn't tear, it doesn't rip apart. It simply curves, following the rules Einstein wrote down, rules that have been tested and confirmed in experiment after experiment, observation after observation. And those rules tell us something profound. The universe is not a static stage. It's dynamic, responsive, alive, in a sense bending and flowing in response to what's in it. Mass and space-time are in constant conversation. Mass shapes space. Space guides motion. And in the most extreme cases, that conversation creates structures so strange, so far beyond everyday experience, that we're still learning how to think about them properly. But Einstein's equations, beautiful as they are, have limits. They describe space-time perfectly at large scales, but they break down at the very center of a black hole, at the singularity where density becomes infinite and space and time lose their meaning. To understand what happens there, we need something more, a theory that blends relativity with quantum mechanics. And that theory, the holy grail of modern physics, doesn't exist yet, not fully, not in a form we can test. Which brings us to the next part of our journey, to the question that's haunted physicists for decades. What really happens as you fall into a black hole? Not just at the horizon where time dilates and you appear to freeze, but deeper in, where the forces grow so strong that they tear matter apart, atom by atom, stretching and compressing in ways that have earned a name, both scientific and darkly whimsical. We've talked about the boundary. Now it's time to cross it and see what waits on the other side. Imagine you have two identical watches, perfect twins, ticking in perfect synchrony. You keep one on your wrist, the other you send on a journey deep into a gravitational well, close to a massive object, where space-time curves sharply. When the traveling watch returns, you compare them, and you discover something impossible. The watch that traveled has fallen behind, not because it malfunctioned, not because it ran slow, but because it experienced less time. Fewer seconds actually passed for it. Time itself moved at a different pace. This isn't science fiction. It's not a thought experiment divorced from reality. It's measurable, testable, and it happens every single day right above your head, in the satellites that help you navigate in the clocks that keep our modern world synchronized. Time is not the constant universal metronome we once believed it to be. It flows at different rates depending on where you are, how fast you're moving, and how deeply you're embedded in a gravitational field. Near a black hole, time doesn't just slow down a little. It crawls, it stretches. It approaches something that looks almost like stillness, though stillness isn't quite the right word. The watch is still ticking, the atoms are still vibrating. But from the perspective of someone far away watching everything near the black hole, seems to be moving through time in slow motion, like a film playing at half speed, then quarter speed, then slower still. Let's start with something tangible, something you can verify right now if you have a smartphone. The Global Positioning System GPS relies on a network of satellites orbiting Earth at about 12,000 miles altitude. Each satellite carries an atomic clock accurate to within nanoseconds. These clocks send timing signals to receivers on the ground, and by comparing the arrival times from multiple satellites, your phone can calculate your position to within a few meters. The whole system depends on those clocks being synchronized with extraordinary precision. A timing error of just 1 microsecond, 1/1,000,000th of a second, would throw off your position by about 1,000 feet. But here's the problem. Those satellites are moving fast, about 8,700 miles per hour, and according to special relativity moving clocks, run slow. That effect, called velocity time dilation, causes the satellite clocks to lose about 7 microseconds per day compared to clocks on the ground. At the same time, the satellites are higher up, farther from Earth's center, in a region where gravity is slightly weaker. And according to general relativity clocks, in weaker gravity run faster. That effect causes the satellite clocks to gain about 45 microseconds per day. The net result: the satellite clocks run about 38 microseconds per day, faster than identical clocks on Earth's surface. That might not sound like much, but if engineers didn't correct for it, if they assumed time was absolute and universal, GPS would accumulate errors of over 6 miles per day. Within a week, the system would be useless. Every GPS satellite has Einstein's equations programmed into its software, adjusting for both special and general relativistic effects. You can navigate to the grocery store because we understand how gravity bends time. Now, let's scale this up, way up. Imagine instead of Earth's gentle gravitational field, you're near a black hole. Not just any black hole, but a stellar mass. Black hole maybe 10 times the sun's weight, with an event horizon about 18 miles across. You're in a spaceship hovering at a safe distance, engines firing to hold position against the inward pull of space-time. Your friend, feeling brave, or perhaps foolish, decides to descend closer to the horizon in a smaller craft. They drop down until they're hovering just a few miles above the event horizon, their own engines screaming to stay in place. You both start with synchronized clocks. After what feels like 1 hour to your friend near the horizon, they climb back up to join you. You compare watches, and you discover that for you, far from the black hole, several hours have passed. Maybe 5, maybe 10. Depending on exactly how close they got time for them, move slower relative to your time. They aged less. They experienced less time. It's not an illusion. It's not a trick of perception. It's a difference in the geometry of space-time. Physicists have a formula for this. The time dilation factor near a non-rotating black hole depends on how close you are to the Schwarzschild radius. At the event horizon itself, the dilation factor becomes infinite. An observer far away would see time at the horizon slow to a stop. 1 second at the horizon would correspond to infinite time for the distant observer. This is why from outside, you never actually see anything cross the event horizon. You see it slow down, asymptotically approaching the boundary, its image dimming and redshifting, but never quite reaching it. Let's put some numbers to this to make it concrete. Suppose you're orbiting a black hole with a mass of 10 suns at a distance of, say, 100 miles from the center. That's comfortably outside the event horizon, which is at about 18.5 miles. At that distance time, dilation is relatively modest. Your clock runs maybe 70% as fast as a clock infinitely far away. But if you drop down to 25 miles from the center, just a bit more than the Schwarzschild radius time, dilation becomes severe. Your clock might run at only 30% the rate of that distant clock. Every hour you experience 3 or 4 hours pass for observers far from the black hole. This creates scenarios that sound like they belong in a time travel story, but are perfectly real physics. Imagine a pair of twins again. One stays on a space station far from a black hole. The other descends close to the event horizon, hovers there for what feels like a year, then returns. When they reunite, the twin who stayed far away has aged decades. Their children are grown. The world has moved on. The twin who descended is only a year older, still young, while their sibling has become elderly. It's not magic, it's geometry. This thought experiment was explored beautifully in the 2014 film Interstellar, which worked with physicist Kip Thorne to get the science as accurate as a Hollywood movie reasonably can. In the film, astronauts visit a planet orbiting close to a massive black hole called Gargantua. They spend a few hours on the planet's surface, and when they return to their ship, they discover that more than 23 years have passed for the crew member who stayed behind. The movie dramatizes, it adds emotion and tension, but the underlying physics is sound. Massive time dilation near a black hole is real, and it's one of the strangest predictions of general relativity. Now, here's a question people often ask. If time slows down near a black hole from an outside perspective, does that mean you'd experience time differently if you were the one falling in? The answer is no. From your own reference frame, your own perspective, time always feels normal. Your heart beats at its usual rate. Your thoughts flow at their usual speed. You don't feel sluggish or slow. It's only when you compare your clock to a distant clock that the difference becomes apparent. This is one of the hardest aspects of relativity to internalize. There's no absolute time, no universal clock ticking in the background of the universe. Time is local, personal, dependent on your path through space-time. Two observers moving along different paths will disagree about how much time has elapsed between two events, and both are correct within their own frames of reference. Let's think about this with another analogy. Imagine two people starting at the same point and walking to the same destination, but taking different routes. One walks straight, the other takes a winding path curving this way and that. When they meet at the destination, they've both arrived, but they've traveled different distances. The straight line walker covered less ground. Neither is wrong. Distance depends on the path you take. Time works the same way in relativity. Two observers starting at the same event and ending at the same event, but traveling along different paths through space-time, will measure different amounts of elapsed time, and both measurements are valid. This has been tested experimentally many times with increasing precision. In 1971, physicists Joseph Hayfel and Richard Keating flew atomic clocks around the world on commercial airliners once eastward and once westward, then compared them to reference clocks that stayed on the ground. The traveling clock showed exactly the time differences predicted by relativity effects measured in nanoseconds, but real and consistent with theory. In 2010, researchers at the National Institute of Standards and Technology measured time dilation over a height difference of just 1 foot. They used the most precise atomic clocks ever built, clocks accurate to 1 part in 10 to the 18th power, and they showed that a clock 1 foot higher above Earth's surface runs faster than a clock 1 foot lower by about 90 billionths of a nanosecond per second. Tiny, yes but measurable, and exactly what relativity predicts. Now apply this to a black hole where the gravitational field is not a gentle slope, but a cliff, a chasm, a plunge into extreme curvature. The gradient of time dilation becomes steep, very steep. If you were hovering at the event horizon and you extended your arm downward toward the singularity, the watch on your hand would tick slower than a watch at your shoulder. The difference would be tiny maybe, but it would be there. Gravity doesn't affect you as a whole. It affects every part of you individually, and parts closer to the black hole experience stronger gravity, deeper time dilation. This gradient, this difference in gravitational pull from one part of an object to another, is called tidal force, and we'll explore its destructive power in more detail soon. But for now, focus on the time aspect. Time isn't just slower near a black hole. It varies across space, creating a gradient, a slope where time flows at different rates depending on your precise position. Think about what this means for communication. Suppose you're far from a black hole safely outside, and your colleague is hovering closer in. You send them a radio message, a simple, "Hello, how are you?" From your perspective, the message travels at the speed of light and arrives almost instantly. But from their perspective, deep in the gravity, well, your message arrives blue-shifted, compressed, faster than it should be. If they reply, their message travels back up toward you, and as it climbs out of the gravity well, it loses energy, redshifts, stretches out. You receive their reply, but it sounds slowed down, distorted like a recording played at half speed. As they get closer to the horizon, this effect intensifies. Their messages take longer and longer to reach you, not because the distance is increasing, but because time near the horizon is so dilated that each second for them corresponds to many seconds, then minutes, then hours for you. Eventually, if they hovered at the very edge of the horizon, their messages would never reach you. They'd be trapped in the time dilation, stretched infinitely lost in the asymptotic approach to the boundary. Here's something even stranger. From their perspective, looking outward, the universe would appear to speed up. Light from distant stars would be blue-shifted. Events that took years in the outside universe would seem to happen in moments. If they could somehow survive falling through the event horizon, which we'll discuss soon, they'd watch the entire future history of the universe play out in fast forward before they reach the singularity. Stars would age and die. Galaxies would evolve. The cosmos would march toward its ultimate fate, compressed into the brief seconds of their fall. Both perspectives, the outside observer seeing the infalling object freeze, and the infalling observer seeing the universe accelerate, are equally valid. They're two views of the same space-time geometry, distorted by the extreme curvature near the black hole. Now, let's talk about a specific example, a real black hole we've observed and studied. Sagittarius A, YGCs. The supermassive black hole at the center of the Milky Way has a mass of about 4 million suns. Its Schwarzschild radius is roughly 7.5 million miles, about 12 million kilometers. Stars orbit it in elliptical paths, and we've been tracking one particular star called S2 for decades. S2 has an orbital period of about 16 years, and its closest approach to Sagittarius A brings it to within about 120 astronomical units, roughly 4 times the distance from the Sun to Neptune. At that closest approach, S2 is moving at about 3% the speed of light, and it's deep enough in the black hole's gravitational field that time dilation becomes measurable. Researchers have calculated that during S2's closest pass, it experiences time running about 30 seconds slower per year compared to Earth's time. Over the course of its 16-year orbit, that adds up to about 8 minutes of lost time relative to us. S2 is effectively a giant cosmic clock orbiting a black hole aging slightly slower than we are all because of the curvature of space-time. This is one of the ways astronomers confirmed that Sagittarius A really is a black hole and measured its mass precisely. By tracking S2's orbit using telescopes equipped with adaptive optics to correct for atmospheric distortion, they mapped out the gravitational field, fit the data to general relativity's predictions, and found a perfect match. The math works, the observations agree. Sagittarius A is real massive and exactly where and how relativity says it should be. But here's a sobering thought. We're safe from Sagittarius A Sewer. We're 26,000 light-years away. The time dilation we experience from it is utterly negligible. But imagine if we were closer. Imagine if Earth orbited a black hole instead of the Sun. Even if we maintained the same orbital distance 93 million miles out, the time dilation would be extreme if the black hole was massive enough. Generations on Earth could watch as the rest of the universe aged and died, stars exhausting their fuel, galaxies fading, everything rushing toward heat death, while we locked in, our time-dilated orbit experienced time crawling by. It's a scenario that appears in science fiction, but it's grounded in real physics. Time dilation isn't just an effect. It's a weapon, a tool, a strange feature of the universe that allows for radically different experiences of duration, depending on where you are and how deeply gravity has its grip on you. Let's consider one more scenario. One that highlights just how extreme time dilation can become. Suppose you decided to orbit as close to a black hole's event horizon as physics allows. You'd need enormous thrust to maintain that orbit fighting constantly against the inward flow of space-time. But let's say you have an impossibly powerful engine. You orbit at, say, 1 millimeter above the horizon. At that distance time, dilation is so extreme that for every second you experience thousands of years pass in the outside universe. You could orbit for what feels like an hour, then climb back out and return to a universe that's aged millennia. Civilizations would have risen and fallen, technologies unimaginable to you would have been invented, used, and forgotten. And if you dared to descend even closer within a fraction of a millimeter, time dilation would approach infinity. You could orbit for what feels like a heartbeat, and the universe outside would age beyond recognition. Stars would burn out. Galaxies would collide and merge. The cosmic microwave background would redshift into nothingness. You'd emerge if you emerged into a cold, dark, distant future, a universe almost unrecognizable. This is the power of time dilation near black holes. It's not subtle. It's not a small correction. It's transformative, dramatic a window into just how flexible and strange space-time really is. Einstein's equations predict it. Observations confirm it. And it means that black holes are not just objects in space. They're objects that warp time itself, creating gradients so steep that the very flow of moments changes depending on where you stand. But time dilation is only part of the story. We've talked about how clocks slow down, how time stretches, how observers disagree about duration. But we haven't yet addressed what happens to you physically as you fall deeper into that gravitational well. Because gravity doesn't just affect time, it affects space and it affects the matter moving through that space. The gradient of gravity, the difference in pull from your head to your feet, creates forces that stretch and compress, forces that grow stronger as you approach the singularity. Forces with a name that sounds almost whimsical until you understand what it describes. Spaghettification, the point where time slows and space tears, where the geometry of the universe stops being gentle and starts being violent. Stand up for a moment. Feel the weight of your body, the gentle pull downward. Now, notice something subtle. Your feet pressed against the floor feel slightly more gravity than your head 6 feet higher. The difference is tiny, unmeasurable without instruments, but it's real. Earth's gravity is slightly stronger at your feet because they're closer to Earth's center. That difference, that gradient from one part of your body to another, is called a tidal force. It's the same force that pulls on the oceans, creating high and low tides as the moon tugs on the water nearest to it more strongly than the water on the far side. Now imagine that gradient not as a whisper, but as a scream. Imagine falling toward a black hole where the difference in gravitational pull between your head and your feet isn't negligible but catastrophic, where the force pulling your feet inward is so much stronger than the force pulling your head that you're stretched, elongated, pulled like taffy until your body tears apart at the molecular level. Physicists have a name for this process, and it's almost playful in its horror. Spaghettification. The transformation of matter into long, thin strands like pasta being pulled through a press. Tidal forces exist anywhere. There's a gradient in gravity anywhere the strength of the gravitational field changes over distance. On Earth, they're gentle. The moon raises tides in our oceans by about 3 feet on average, pulling the water into an oval shape, one bulge facing the moon, one on the opposite side. The sun contributes too, though less so because it's farther away. When the sun and moon align during new and full moons, their tidal forces combine, creating spring tides, higher highs, and lower lows. When they're at right angles during the quarter moons, their forces partially cancel, creating neap tides more moderate. But tidal forces near a black hole are not moderate. They're extreme, violent, lethal. Let's walk through what happens step by step. As you fall toward a stellar mass black hole, one with perhaps 10 times the sun's mass and a Schwarzschild radius of about 18 miles. At first, far from the black hole, maybe hundreds of miles out, the tidal force is mild. You feel acceleration, a pull inward, but it's uniform across your body. You're in free fall, weightless, like an astronaut in orbit. Everything feels normal, but as you fall closer, the gradient begins to grow. Your feet being closer to the singularity feel a stronger pull than your head. The difference is small at first, maybe a few percent. Uncomfortable perhaps, like being stretched on a rack, but survivable. As you continue to fall, approaching the event horizon, the gradient intensifies. The pull on your feet increases exponentially compared to the pull on your head. Your spine lengthens, your bones creak, your muscles strain. At some point, the difference in force exceeds what your body can withstand. Bones snap. Tissue tears. You're being pulled apart not by any external object, but by the shape of space-time itself, by the simple fact that different parts of your body are experiencing different strengths of gravity. And it gets worse. Not only are you stretched vertically from head to feet, but you're also compressed horizontally. Think of it like this. As you fall toward the singularity, everything around you is also falling toward the same point. Objects to your left and right are being pulled inward toward the center, which means they're being pulled toward you from the sides. You're squeezed from the sides while being stretched from top to bottom. Your body becomes thinner, longer, deformed, into a shape that barely resembles human anymore. At the atomic level, the forces become incomprehensible. The bonds holding molecules together, the electromagnetic forces binding atoms into structures they have limits. When the tidal force exceeds those limits, molecules break apart. Your body, once a cohesive structure of cells and organs, becomes a stream of atoms stretched into a narrow column, falling inward. You're no longer a person. You're a string of matter still containing the same atoms you started with, but rearranged into a form unrecognizable. This is spaghettification. And the term coined in the 1970s is both scientifically accurate and gruesomely evocative. You're literally turned into spaghetti, a long, thin strand before being pulled into the singularity. Now, here's something crucial. When this happens, depends entirely on the size of the black hole. For a stellar mass black hole with a mass of around 10 suns, the tidal forces become lethal well before you reach the event horizon. You'd be torn apart, perhaps hundreds of miles outside the horizon, dying in the empty space around the black hole, never making it to the boundary. Your remains would continue falling, of course, a stream of atoms spiraling inward, but you as a conscious being would be gone long before crossing the point of no return. But for a supermassive black hole, the kind that lurks at the centers of galaxies, the story changes dramatically. These black holes have masses of millions or billions of suns, and their event horizons are correspondingly enormous. Sagittarius A Xiang, with 4 million solar masses, has an event horizon radius of about 7.5 million miles. At that scale, the curvature of space-time is gentler. The gradient of gravity, though still present, is spread out over a much larger region. And here's the surprising part. You could cross the event horizon of a supermassive black hole and still be alive, still intact, still conscious. Let's think about why. Tidal force depends on the gradient, the rate at which gravity changes over distance. For a small black hole, the gradient is steep. Gravity increases rapidly as you get closer. For a large black hole, the gradient is gentler. Gravity still increases, but more gradually. At the event horizon of Sagittarius A, the tidal force would be noticeable, uncomfortable perhaps, but not immediately lethal. You could in principle cross the horizon, look around, experience being inside a black hole, at least for a little while, before the tidal forces deeper and eventually destroyed you. This difference between stellar mass and supermassive black holes is one of the most common misconceptions people have. They imagine all black holes as instant death traps tearing apart anything that comes near. But size matters. A supermassive black hole's event horizon is not a violent boundary. It's a quiet edge, a place you could cross without even realizing it, at least not immediately. Imagine the scenario. You're falling into Sagittarius A. You've crossed the event horizon. From your perspective, nothing dramatic happened at the moment of crossing. Space looks the same. Time feels the same. But you know intellectually that you've passed the point of no return. Every direction you could move now leads inward. You look around. Behind you, you'd see the universe compressed into a bright circle, the light from billions of stars blue-shifted and concentrated. Ahead of you, darkness. The singularity is still far away, perhaps millions of miles deeper in, but it's inevitable. You're falling toward it, and nothing can change that. How long would you survive? It depends on how fast you're falling and how much time passes before the tidal forces grow strong enough to kill you. For Sagittarius, scientists have estimated that you might survive for several minutes, perhaps even an hour inside the event horizon before being torn apart. That's a strange thought, isn't it? An hour to contemplate your fate, to experience being inside a black hole, to observe the geometry of space-time from a perspective no one has ever had and lived to describe. Of course you wouldn't live to describe it. There's no coming back. No signal you send, no light you shine will ever escape. You're cut off from the universe, falling alone through a region of space-time that's sealed off from everything outside. Let's quantify this a bit. The tidal force on an object depends on its size and the gradient of the gravitational field. For a human body roughly 6 feet tall, falling feet first toward a black hole, the tidal force can be approximated by the difference in gravitational acceleration between your feet and your head. Near a 10 solar mass black hole at the event horizon, that difference is enormous enough to exert forces thousands of times, your body weight pulling your feet down and your head up. You'd be ripped apart almost instantly. But near a 4 million solar mass black hole like Sagittarius AI, at the event horizon, the tidal force is much smaller, perhaps comparable to the force you'd feel if you were hanging from a bar on Earth. Uncomfortable, but survivable at least for a while. The force increases as you fall deeper, and eventually it becomes lethal, but not immediately at the horizon. This has interesting implications for the question of whether anything could survive inside a black hole even briefly. The answer is yes for large enough black holes. You wouldn't survive long, and you'd have no way to communicate your experience, but there would be a window, a brief span of time where you'd be inside the event horizon alive, aware, experiencing something no human has ever experienced. Now, let's talk about what spaghettification looks like from outside. Suppose you're watching a probe fall into a stellar mass black hole, and the probe is equipped with cameras and sensors. As it approaches the event horizon, you see it start to stretch. The image distorts, elongates. Light from the probe redshifts dimming. The probe appears to slow down, time dilation taking hold. And as it nears the horizon, you see it stretched into a thin line, a thread of matter, before it fades from view, locked at the horizon from your perspective. But from the probe's perspective, it fell through in seconds, experiencing the violent tidal forces being torn apart, destroyed. The two perspectives, yours and the probe's, tell different stories, but both are true. The probe never crosses from your point of view. It crosses and is destroyed from its own point of view. Relativity allows both to be correct. There's a fascinating historical note here. The term spaghettification wasn't used in the early days of black hole research. Scientists referred to it more formally as tidal disruption or tidal stretching. But in the 1970s, as black holes became a topic of public interest, popularizers of science started using more evocative language. Stephen Hawking, in his lectures and books, sometimes used the term to help audiences visualize the process, and it stuck. Now, even in professional papers, you'll occasionally see the word spaghettification, a reminder that science doesn't always have to be dry and formal to be accurate. Let's consider a real-world example of tidal disruption, not of a person, but of a star. Astronomers have observed events called tidal disruption events, or TDEs, where a star wanders too close to a supermassive black hole and is torn apart by tidal forces. The star held together by its own gravity, and the pressure of fusion can't withstand the gradient. It's stretched into a stream of gas, which then spirals into the black hole, heating up and emitting a bright flare of X-rays and ultraviolet light. These events are rare, maybe one per galaxy, per 10,000 years, but when they happen, they're spectacular. In 2011, astronomers observed a TDE in a galaxy about 3.8 billion light-years away. A star probably similar in size to our Sun drifted too close to a black hole with a mass of about 1 million suns. The star was torn apart, and as the gas fell into the black hole, it released energy equivalent to 1 billion suns shining for several months. We saw the flare from across the universe, a beacon announcing the death of a star. What's remarkable is that we can use these events to study black holes that are otherwise invisible. The black hole itself emits no light, but the process of tidal disruption creates a temporary accretion disk, a swirl of superheated gas that shines brightly. By studying the spectrum of that light, the way it changes over time, astronomers can measure the black hole's mass, its spin, even the composition of the star that was destroyed. Tidal forces also shape the environments around black holes in more subtle ways. Material falling toward a black hole doesn't usually fall straight in. It has angular momentum, a bit of sideways motion, and as it spirals inward, conservation of angular momentum causes it to spin faster and faster, forming an accretion disk. Within that disk, gas particles collide. Friction heats them up, and they emit radiation. The innermost regions of the disk closest to the event horizon reach temperatures of millions of degrees hot enough to glow with X-rays. But the tidal forces in the disk are also tearing it apart. The inner edge of the disk is constantly being pulled inward while the outer edge is more stable. The disk is dynamic, turbulent, a chaotic dance of gravity and motion. Jets of material, accelerated to nearly the speed of light, sometimes blast outward from the poles of the black hole perpendicular to the disk. We don't fully understand how these jets form, but tidal forces and magnetic fields both play a role. Here's a question worth considering. If you could choose, would you rather fall into a stellar mass black hole or a supermassive one? The stellar mass black hole would kill you quickly, tearing you apart in seconds before you even reach the event horizon. The supermassive black hole would let you cross the horizon, give you time to think, to observe, but the end would be the same. You'd eventually be spaghettified, deeper inside. Which would you choose, a quick, violent death or a slower, more contemplative one with the same inevitable conclusion? There's no right answer, of course, but the question highlights the strange choices the universe presents when you push physics to its limits. Spaghettification is ultimately a reminder that black holes are not gentle. They're regions of space-time so warped, so extreme, that the normal rules of matter and structure break down. Your body evolved over billions of years to withstand Earth's gentle gravity, has no defense against the gradients near a black hole. You're made of molecules, and molecules have limits. Cross those limits, and you cease to be a coherent structure. But here's the deeper question. What happens after spaghettification? Once you've been reduced to a stream of atoms falling inward, what awaits at the center? We've talked about the event horizon, the boundary of no return. We've talked about the tidal forces that stretch and compress, but we haven't yet addressed the destination, the singularity, the point at the very center of the black hole, where according to Einstein's equations, space-time curvature becomes infinite, and the laws of physics as we know them cease to apply. That's where we're headed, into the deepest mystery, the place where our understanding ends, and the universe keeps one last secret. There's a place in mathematics where numbers stop making sense. Divide by zero, and your calculator throws an error. The operation is undefined. Infinity isn't a number you can work with. It's a signpost that says, the rules break down here. In the mathematics of black holes, that signpost appears at the very center, at a point called the singularity. All the mass that collapsed to form the black hole, all the matter that has fallen in, since crushed down to infinite density in zero volume. A point where space-time curvature becomes infinite, where the equations of general relativity produce infinities, and where physicists must admit reluctantly that we don't know what really happens. The singularity is the ultimate mystery at the heart of every black hole. We can't see it. We can't measure it. We can't even describe it with the physics we have. And that makes it both frustrating and fascinating, a question mark at the center of our most extreme predictions about the universe. Let's start with what the equations tell us. According to general relativity, once matter collapses past the event horizon, it continues falling inward. There's no force that can stop it, no pressure that can hold it up. The geometry of space-time itself compels everything to move toward the center. And at the center, all that matter, all that mass accumulates in a single point. Not a small sphere, not a dense ball, a point. Zero radius, infinite density. A mathematical singularity. Now, physicists don't take this literally. Infinity in physics is almost always a sign that your theory has reached its limits, that you're missing something. When your equations give you infinity, it means you've asked a question the theory can't answer. It's like trying to use Newton's laws of motion at speeds close to light. The equations break down. You need relativity. Similarly, general relativity breaks down at the singularity. You need something else, something we don't have yet. A theory of quantum gravity. But before we talk about what might replace the singularity in a more complete theory, let's explore what relativity does predict. Because even if the singularity is a placeholder for something we don't understand, it tells us important things about the structure of space-time. In 1965, a young physicist named Roger Penrose proved something remarkable. He showed that under very general conditions, once an event horizon forms, a singularity is inevitable. You can't avoid it. It's not a matter of how the matter collapses or what it's made of. The The geometry of space-time inside the event horizon is such that all paths, all possible futures lead to the singularity. Penrose's singularity theorem was a watershed moment. It meant that singularities weren't just artifacts of special, overly simplified models. They were real features of general relativity, unavoidable consequences of the theory. A few years later, Penrose collaborated with Stephen Hawking to extend the result. Hawking showed that the same logic applied to the entire universe running backward in time. If you trace the expansion of the universe back far enough, you reach a singularity, the Big Bang. The beginning of space-time itself. These theorems didn't tell you what the singularity was, but they proved it had to be there, lurking in the equations. Penrose received the Nobel Prize in Physics in 2020 in part for this work. The prize citation noted his use of mathematical methods to show that black hole formation is a robust prediction of general relativity. It was a recognition that singularities, strange as they are built into the fabric of Einstein's theory. Now, let's talk about what kind of singularity exists inside a black hole, because it's not as simple as a point in space. For a non-rotating black hole, the Schwarzschild solution, the singularity is indeed a point. But real black holes rotate, they spin. And for a rotating black hole described by a solution found by Roy Kerr in 1963, the singularity is different. It's not a point, it's a ring. Imagine a donut, but infinitely thin, with all the mass concentrated in a circle. That's the ring singularity of a Kerr black hole. And here's where things get strange. In principle, you could fall through the ring. The mathematics allows it. You'd pass through the center of the donut, emerging on the other side into a region of space-time that some solutions suggest might connect to another universe or to a different part of our own universe far away. This has fueled endless speculation about black holes as wormholes, gateways to other places or times. And the mathematics taken at face value does allow these possibilities. But there's a catch, a huge catch. These solutions are unstable. The slightest perturbation, the tiniest bit of infalling matter, would destabilize the structure. The ring singularity would likely collapse into something else, or the geometry would shift in ways we can't predict. And even if it didn't, crossing through would require surviving the intense tidal forces near the singularity, which, as we've discussed, would tear you apart at the atomic level. So, while the idea of black holes as portals is mathematically intriguing, there's no physical evidence it's real, and plenty of reasons to think it's not. The singularity is more likely a signal that our theory is incomplete than a literal description of reality. Let's consider what happens at the singularity according to the equations, even if we don't take it literally. As you fall inward past the event horizon, space-time curvature increases. The tidal forces grow stronger. Time and space trade roles, in a sense. Outside the horizon, you can move freely in space, but are dragged forward in time. Inside the horizon, you can't avoid moving inward in space, but the singularity is in your future, inevitable, like tomorrow is inevitable for someone sitting on Earth. The closer you get to the singularity, the more extreme the curvature becomes. Distances contract. Time from your perspective continues flowing, but the geometry around you warps beyond comprehension. Eventually, you reach a point where the equations say space-time curvature is infinite. That's the singularity, and that's where physics as we currently understand it stops. Here's a common misconception. People sometimes think the singularity is at the center of the black hole in space, like the core of a planet. But inside the event horizon, the singularity isn't a place. It's a moment in time. It's in your future, unavoidable, the end of your timeline. You can no more avoid reaching the singularity than you can avoid reaching next Tuesday. It's not a question of where you are, but when. This is one of the most mind-bending aspects of black hole geometry. The singularity is not a point you could in principle steer around or avoid. It's a moment you will reach no matter what you do, as long as you're inside the horizon. All your possible futures converge there. Now let's talk about what might really be at the center of a black hole, because physicists don't believe the singularity is the end of the story. General relativity is a classical theory, meaning it doesn't account for quantum mechanics, the physics of the very small. At everyday scales, even at the scale of stars and galaxies, quantum effects are negligible. But at the singularity where matter is compressed to infinite density, quantum mechanics should matter a lot. The problem is, we don't have a complete theory of quantum gravity. General relativity describes gravity beautifully at large scales. Quantum mechanics describes particles and forces beautifully at small scales. But the two theories don't fit together neatly. They use different mathematical languages, different assumptions. Attempts to merge them to create a theory of quantum gravity have been ongoing for decades. And while progress has been made, we're not there yet. String theory is one candidate. It proposes that particles aren't point-like, but are tiny vibrating strings, and that space-time has extra dimensions we don't perceive. In string theory, the singularity might be replaced by a small but finite region, a fuzzball of strings avoiding the infinity problem. Loop quantum gravity is another approach. It suggests that space-time itself is made of discrete units, tiny loops, and at the singularity, these loops prevent infinite curvature. The singularity becomes a quantum bounce, or a region of extreme but finite density. These are speculative ideas still being developed and tested mathematically. We have no experimental evidence to confirm them, because we can't observe the inside of a black hole. But they point to a deeper truth. The singularity as predicted by general relativity is probably not the final answer. It's a placeholder, a sign that we need new physics. There's also the question of what's called cosmic censorship. This is a conjecture proposed by Roger Penrose in 1969, which states that singularities are always hidden behind event horizons. In other words, nature doesn't allow naked singularities, singularities that are visible to the outside universe. If a singularity formed without an event horizon, it would be a place where physics breaks down visible to observers, which would be deeply troubling. It would mean the universe could produce unpredictable, uncontrollable regions where anything could happen. The cosmic censorship conjecture suggests this doesn't happen. Every singularity is clothed by an event horizon hidden from view, and so far all the black holes we've observed fit this pattern. We've never seen a naked singularity. But proving the conjecture mathematically has been difficult. There are exotic scenarios edge cases in the equations where naked singularities might form. Whether they actually do in the real universe remains an open question. Let's think about what this means for someone falling into a black hole. You cross the event horizon. From that moment, the singularity is in your future unavoidable. As you fall deeper, tidal forces intensify, stretching and compressing you. At some point, you're torn apart. Your atoms, now separated, continue falling. They approach the singularity. And then what? According to general relativity, they're crushed to infinite density. But according to quantum mechanics, something else probably happens. Maybe the atoms are converted into some exotic form of matter, or energy or information that we don't have words for yet. Maybe space-time itself undergoes a transition, becoming something that isn't space or time in the way we understand those concepts. We simply don't know, and that not knowing is humbling. It's a reminder that the universe still holds secrets beyond our current grasp. Here's another intriguing aspect. Black holes are among the simplest objects in the universe in one sense. They're described by just a few properties: mass, spin, and electric charge. A theorem in general relativity, sometimes called the no-hair theorem, states that black holes have no other distinguishing features. Two black holes with the same mass, spin, and charge are identical no matter what kind of matter formed them. You could make a black hole from hydrogen or iron or old encyclopedias, and as long as the mass, spin, and charge are the same, the resulting black hole would be indistinguishable. This is strange when you think about it. All the complexity, all the information about what fell into the black hole seems to disappear. A star with its layers and composition and history collapses into a black hole described by three numbers. Where did the information go? This is called the black hole information paradox, and it's been a major puzzle in theoretical physics for decades. Stephen Hawking contributed to this problem in 1974 when he discovered that black holes aren't entirely black. They emit radiation now called Hawking radiation due to quantum effects near the event horizon. Over incredibly long time scales, this radiation causes black holes to evaporate, shrinking slowly until they disappear entirely. A solar mass black hole would take about 10 to the 67th years to evaporate, far longer than the current age of the universe, but the principle stands. Black holes are not eternal. But here's the problem. Hawking radiation, as originally calculated, appears to be completely random, carrying no information about what fell into the black hole. If the black hole evaporates completely, that information is lost, which violates a principle of quantum mechanics that says information is always conserved. This paradox has sparked fierce debates and deep research. Some physicists think information is encoded in the Hawking radiation in ways we don't yet understand. Others think it's stored somehow in the structure of space-time. The question is still unresolved. What strikes me about all this is the honesty of physics at its edges. Scientists could pretend they understand the singularity, invent stories, declare certainty. But they don't. They admit the limits. They say, here are equations give infinity, and we know that means we're missing something. That humility, that willingness to acknowledge gaps in knowledge is one of the most beautiful aspects of science. The singularity is a boundary not of space, but of understanding. It's the place where our best theories fail, where we're forced to confront the fact that the universe is deeper and stranger than we currently comprehend. And rather than being a weakness, that's a strength. It tells us where to focus our efforts, where the next breakthroughs might come. For now, the singularity remains hidden, cloaked behind the event horizon, inaccessible to observation or experiment. We can't send a probe to explore it. We can't see it directly. We can only infer its presence through mathematics and through the effects black holes have on their surroundings. But those effects are real, observable, and spectacular. Black holes, despite hiding singularities, we don't fully understand, interact with the universe in measurable ways. They warp space-time. They bend light. They accelerate matter to incredible speeds. And when two black holes collide, they send ripples through space-time. It's self-ripples we've learned to detect, opening a new window into the most violent events in the cosmos. That's where our journey turns next, to the moments when black holes merge, and announce their union with a symphony of gravitational waves that echo across the universe. Imagine the fabric of space-time as a perfectly still pond, smooth and undisturbed. Now, drop a pebble into the water. Ripples spread outward in these concentric circles, carrying energy away from the point of impact, traveling across the surface until they fade into the distance. Einstein predicted in 1916 that massive objects accelerating through space would create ripples in space-time itself, waves of gravity spreading outward at the speed of light. He called them gravitational waves, and he thought we'd never be able to detect them. The ripples he calculated would be unimaginably faint by the time they reached Earth, too subtle for any instrument to measure. For 100 years, he was right. Gravitational waves remain theoretical, predicted by mathematics but never observed, until September 14, 2015, when two massive detectors separated by thousands of miles felt space-time itself shiver and ring like a bell struck by an invisible hammer. The source was 1.3 billion light-years away. Two black holes locked in a death spiral had collided and merged, and the ripples from that collision, traveling across the cosmos for over 1 billion years, finally washed over Earth, stretching and squeezing space by less than the width of a proton. The detection was announced in February 2016, and it changed everything. For the first time, we weren't just seeing the universe, we were hearing it. A new sense had opened, Astronomy had become multisensory. Let's walk through what gravitational waves are because the concept is subtle and beautiful. When a mass moves, it distorts the space-time around it. If the mass moves smoothly at constant velocity, the distortion moves with it, but nothing ripples outward. But if the mass accelerates, if it speeds up, slows down, or changes direction, the changing distortion creates waves, disturbances that propagate through space-time at light speed. The stronger the acceleration and the more massive the object, the stronger the waves. Everyday objects, even large ones like cars or buildings, produce gravitational waves so weak that they're completely undetectable. Even the Earth orbiting the Sun produces waves, but they're vanishingly small. To create gravitational waves strong enough to detect across interstellar distances, you need something extreme, something like two black holes each dozens of times the mass of the Sun, orbiting each other at a significant fraction of light speed, spiraling inward, and finally colliding. That's exactly what happened in the event called GW10914, the first gravitational wave detection. The two black holes had masses of about 36 and 29 times the Sun. They had been orbiting each other for billions of years, slowly losing energy to gravitational wave radiation, spiraling closer and closer. In the final moments, they were orbiting each other hundreds of times per second, moving at speeds approaching half the speed of light. And then they merged, combining into a single black hole with a mass of about 62 solar masses. Wait, 36 plus 29 equals 65. But the final black hole was only 62 solar masses. Where did the missing 3 solar masses go? They were converted into energy, pure energy. In a fraction of a second, 3 times the mass of the Sun, converted into gravitational waves, radiated outward into the universe. Einstein's equation, E equals mc squared, tells us that even a small amount of mass contains enormous energy. 3 solar masses is equivalent to about 5.4 times 10 to the 47th joules. That's more energy than the Sun will radiate over its entire 10 billion year lifetime, released in a fraction of a second. During the peak of the merger, for just a brief moment, the power output in gravitational waves exceeded the combined light output of all the stars in the observable universe. Think about that. All the hundreds of billions of galaxies, each containing hundreds of billions of stars, all their light added together, and this single event outshone them all, though not in light, but in gravitational waves. And yet, by the time those waves reached Earth, they were faint. Unbelievably faint. The detectors that caught them, called LIGO Laser Interferometer Gravitational Wave Observatory, are the most sensitive instruments ever built. They can measure changes in distance smaller than 1/10,000th the diameter of a proton. To put that in perspective, if the distance from Earth to the nearest star, Proxima Centauri, about 4 light-years, were scaled down to the width of a human hair, LIGO could detect a change smaller than an atom. LIGO consists of 2 L-shaped detectors, one in Hanford, Washington, the other in Livingston, Louisiana, separated by about 900 miles. Each arm of the L is about 2.5 miles long. Laser beams travel down the arms, bounce off mirrors, and return. When a gravitational wave passes through it, stretches space in one direction, and compresses it in the perpendicular direction, the laser beams detect this stretch and squeeze, interfering with each other in a way that reveals the passing wave. The idea for LIGO began in the 1970s and 80s, championed by physicists Rainer Weiss, Kip Thorne, and Barry Barish. They proposed building detectors sensitive enough to catch gravitational waves from cosmic events. The project was ambitious, expensive, and many scientists doubted it would work. Gravitational waves were still theoretical. No one had detected them directly. Building billion-dollar instruments to hunt for something that might not exist or might be too faint to measure seemed risky. But they persevered. Construction began in the 1990s. The first generation of LIGO operated from 2002 to 2010 and detected nothing. The instruments weren't sensitive enough, so they upgraded building advanced LIGO with improvements that increased sensitivity by a factor of 10. Advanced LIGO began operations in September 2015, and just days after turning on September 14, 2015 at 5:51 a.m. Eastern Time, the detectors caught GW1500914. The signal was so clear, so strong, that researchers initially thought it might be a test, an artificial signal injected into the system to check if the analysis software worked properly. But it wasn't. It was real. Two black holes colliding 1.3 billion years ago, announcing their merger to the universe. The waveform, the shape of the signal, matched the predictions of general relativity almost perfectly. Scientists had run computer simulations for years, modeling how black holes would spiral together, how the space-time around them would ripple what the gravitational wave signal should look like. And here it was, in the data, unmistakable. A chirp starting at low frequency, sweeping upward as the black holes accelerated, then cutting off abruptly at the moment of merger. It sounded, when converted to audio, like a rising tone, a cosmic chirp. When the discovery was announced in February 2016 at a press conference broadcast around the world, scientists openly wept. A century of theoretical prediction, decades of engineering, years of patient observation had finally paid off. Gravitational waves were real. Einstein had been right. In 2017, Weiss, Thorne, and Barish were awarded the Nobel Prize in Physics for the detection. The prize recognized not just the discovery, but the extraordinary effort required to make it the vision to pursue something that seemed almost impossible. Since that first detection, LIGO has observed dozens more gravitational wave events, black hole mergers mostly, but also neutron-star mergers. In 2017, LIGO detected two neutron stars colliding in an event called GW170817. This one was special because it also produced light. Telescopes around the world, alerted by the gravitational wave signal, turned to the location and saw an explosion of kilonova as the neutron stars merged and flung heavy elements into space. It was the first time an event was observed in both gravitational waves and light, the beginning of multi-messenger astronomy. The neutron-star merger taught us something profound. Heavy elements like gold and platinum aren't made in ordinary supernovae. They're made in neutron-star collisions. When two neutron stars merge, the intense conditions create rapid neutron capture processes, building up heavy nuclei in a matter of seconds. The gold in your ring, the platinum in catalytic converters were forged in collisions like this billions of years ago, then scattered into space to eventually become part of planets and people. Gravitational waves let us study events that are completely invisible in light. Black hole mergers, for instance, produce no light. They're dark, silent in the electromagnetic spectrum. But in gravitational waves, they're loud, clear, unmistakable. We can measure the masses of the black holes, their spins, the distance to the event, all from the waveform. One of the remarkable things about gravitational waves is how cleanly they travel. Light passing through space can be absorbed, scattered, distorted by dust and gas. Gravitational waves pass through everything essentially undisturbed. They carry information from the source across billions of light years without degradation. It's like having a clear window into the most violent events in the universe. Let's talk about what happens during a black hole merger in more detail. Two black holes born from the deaths of massive stars are orbiting each other. Maybe they formed as a binary star system, two massive stars that lived and died together. Or maybe they found each other later, captured by gravity in a dense stellar environment. Either way, they're locked in orbit, and over time they lose energy. How do they lose energy? Through gravitational wave radiation. As they orbit, they're accelerating, constantly changing direction. And that acceleration generates waves. Those waves carry energy away from the system, causing the orbit to shrink. The process is slow at first. Over millions or billions of years, the black holes spiral closer. But as the orbit shrinks, they move faster, and the gravitational wave emission increases. The process accelerates. In the final minutes, the orbit is tight, the black holes racing around each other at incredible speeds. The gravitational waves grow stronger, carrying away more and more energy. The orbit shrinks faster. In the last seconds, the black holes are a blur, whipping around each other hundreds of times per second, emitting a crescendo of gravitational waves, a cosmic scream that peaks at the moment of merger. When they finally collide, the event horizons touch merge, and the two black holes become one. The new black hole is distorted, wobbling, ringing like a struck bell. It settles down quickly within milliseconds into a smooth, spherical event horizon. And the gravitational waves from that final ring down carry away the last bit of excess energy. The entire process from the final minutes of inspiral to the merger and ring down is encoded in the gravitational waveform. By analyzing the signal, scientists can reconstruct what happened, measure the masses and spins, and test whether the merger follows the predictions of general relativity. So far, every event has matched the theory. Einstein's equations, written in 1915, describe black hole mergers in 2015 and beyond, with perfect accuracy. Here's something that still amazes me. The energy released in these mergers is staggering, and it's released in a form we can barely interact with. Gravitational waves pass through your body all the time from distant cosmic events, and you don't feel them. They stretch and squeeze space by infinitesimal amounts, but matter just moves with the space so you don't notice. Only with instruments like LIGO, designed specifically to measure those tiny changes, can we detect them. There's a common misconception that gravitational waves are like sound waves traveling through space as a medium. But space isn't a medium. It's the thing that's waving. Gravitational waves are ripples in the geometry of space-time itself. They don't move through space. They are distortions of space moving at the speed of light. Another misconception is that only black holes produce detectable gravitational waves. Neutron star mergers produce them too, as do supernovae, though those are harder to detect because the waves are weaker. Even the Big Bang itself likely produced gravitational waves, a background hum filling the universe, though we haven't detected that primordial signal yet. It's one of the goals of future observatories. LIGO's success has inspired new detectors. Virgo in Italy joined the search in 2017. Kagra in Japan came online in 2020. Together, these detectors form a network, allowing scientists to triangulate the source of gravitational waves more precisely. The more detectors, the better the localization. The easier it is to point telescopes at the right part of the sky to look for light from the event. There are plans for space-based detectors too. LISA, the Laser Interferometer Space Antenna, is a proposed mission that would place 3 spacecraft in orbit around the Sun, separated by millions of miles, forming a giant detector in space. LISA would be sensitive to lower frequency gravitational waves from events like supermassive black hole mergers at the centers of galaxies. These are events LIGO can't detect because its arms are too short to measure such long wavelength waves. Imagine in the future a network of gravitational wave detectors spanning Earth and space, constantly listening to the universe, catching dozens of events per day, building a catalog of black hole and neutron star populations, measuring the expansion rate of the universe, testing general relativity in extreme conditions. We're at the beginning of a new era, the era of gravitational wave astronomy, and here's the deeper significance. For all of human history, we've observed the universe through light electromagnetic radiation in all its forms. Radio waves, microwaves, infrared, visible light, ultraviolet X-rays, gamma rays. All photons, all variations of the same phenomenon. Gravitational waves are something completely different. They're distortions of space-time ripples in the fabric itself. Detecting them is like gaining a new sense, a way to perceive the universe that doesn't rely on light at all. What might we discover with this new sense? What events are happening in the universe that produce no light but scream in gravitational waves? We've already found black hole mergers we never would have known about otherwise. What else is out there waiting to be heard? Gravitational waves also give us a way to test general relativity in its most extreme predictions. Black hole mergers are the strongest gravitational events in the universe aside from the Big Bang. The space-time around colliding black holes is curved more severely than anywhere else we can observe. And the fact that the waveforms match Einstein's predictions down to tiny details tells us that relativity holds even in these extreme conditions. It's a triumph of theory, a confirmation that our understanding of gravity, strange as it seems, is correct. But there are still mysteries, still questions. Black holes, despite everything we've learned, still hide secrets we can't access locked behind event horizons, buried in singularities we don't fully understand. Gravitational waves let us observe their outsides, their mergers, their dances through space-time. But the interiors remain hidden, inaccessible, theoretical. And that brings us to the final question, the one we've been circling throughout this journey. What are black holes really? Not just mathematically, not just as solutions to equations, but fundamentally. Are they ending's final tombs where matter disappears forever? Or are they transformations, places where the universe changes the rules, where something new and strange emerges? The answer, or at least the beginning of one, might lie in a discovery. Stephen Hawking made in the 1970s, a discovery that suggested black holes aren't quite as black as we thought, and that they might, over unimaginable stretches of time, evaporate, leaving behind only questions and light. Black holes are not forever. That sentence sounds wrong, doesn't it? These objects are so massive, so gravitationally dominant, that nothing, not even light, can escape them. They seem like the ultimate permanent fixtures of the universe, eternal prisons from which there is no release. But in 1974, a young physicist named Stephen Hawking discovered something that changed everything. Black holes, he realized, emit radiation. They glow very faintly with a form of thermal radiation that comes from quantum effects near the event horizon. And over unimaginable stretches of time, this radiation causes black holes to shrink, to evaporate, to eventually disappear completely, leaving behind nothing but the faintest whisper of light. Hawking radiation is one of the most elegant and surprising predictions in theoretical physics, and it emerges from the marriage of quantum mechanics and general relativity. Two theories that don't always play nicely together. Let's explore how it works, because the mechanism is beautiful and strange. Quantum mechanics tells us that empty space isn't truly empty. It's filled with what physicists call vacuum fluctuations, pairs of particles and antiparticles that spontaneously pop into existence, exist for a fleeting moment, and then annihilate each other. These are called virtual particles, and they're constantly appearing and disappearing everywhere in the universe, even in the emptiest regions of space. Normally, they have no lasting effect. They appear, they vanish, and the net energy remains zero. But near the event horizon of a black hole, something unusual happens. Imagine a particle-antiparticle pair appearing right at the edge of the horizon. One particle falls into the black hole, crossing the event horizon and disappearing forever. The other particle escapes, flying away into space. From the outside, it looks like the black hole has emitted a particle. And because energy must be conserved, the black hole must lose a tiny bit of mass to account for that escaping particle. This is Hawking radiation. The black hole radiates particles very slowly, very faintly, and in doing so, it loses mass. Over time, this process causes the black hole to shrink. The smaller it gets, the faster it radiates, and the faster it loses mass. Eventually, in a final burst of energy, the black hole evaporates completely, leaving nothing behind. How long does this take? For a stellar mass black hole with 10 times the sun's mass, the evaporation time is about 10 to the 67th years. That's a 1 followed by 67 zeros, a number so vast that it's almost meaningless. For comparison, the current age of the universe is about 13.8 billion years, which is 10 to the 10th years. A black hole would take 10,000 trillion years to evaporate. Long after every star has burned out, long after galaxies have dispersed, long after the universe has gone dark and cold, black holes will still be sitting there, radiating faintly, slowly fading. For supermassive black holes, the timescales are even more absurd. A black hole with 1 billion solar masses would take 10 to the 98th years to evaporate. These are numbers that stretch the imagination beyond its limits. But the principle stands. Black holes are not eternal. They're temporary, at least on cosmic timescales. Hawking's discovery was revolutionary, but it also created a problem, a paradox, that has haunted theoretical physics for decades. The information paradox. Quantum mechanics insists that information is never destroyed, that the state of a system at one time determines its state at all future times. But if a black hole evaporates, completely radiating away as random thermal radiation, what happens to the information about everything that fell into the black hole? All the stars, all the gas, all the detailed structure of what collapsed to form it. Where does that information go? According to Hawking's original calculation, the radiation is completely thermal, meaning it's random, carrying no information. If that's true, then the information is lost, destroyed, which violates quantum mechanics. This is the black hole information paradox, and it's been debated fiercely for over 40 years. Some physicists think the information is encoded in the Hawking radiation in subtle ways we don't yet understand. Others think it's stored in the structure of the event horizon itself, perhaps in some quantum mechanical way that we can't currently describe. Still others think the paradox points to a deeper flaw in our understanding, a sign that we need a complete theory of quantum gravity to resolve it. In recent years, progress has been made. In 2004, Hawking himself revised his position, conceding that information probably is preserved, though the mechanism remains unclear. The debate continues, and it's one of the driving forces behind research into quantum gravity string theory and the fundamental nature of space-time. But let's step back from the paradoxes and the technical details and think about what Hawking radiation means philosophically. It means that black holes, these seemingly inescapable prisons, these endpoints of matter's journey, are not truly final. They're temporary structures, waypoints in the universe's long evolution toward equilibrium. Everything that falls into a black hole will eventually be returned to the universe, albeit in a form so scrambled, so transformed, that its original identity is lost. There's something almost poetic about that. Matter falls into darkness, is held there for eons beyond comprehension, and then slowly is released back into the light, not as stars or planets or people, but as radiation, as energy, as photons, carrying warmth into the cold void. Black holes also remind us of the limits of knowledge. We have learned so much about them, measured their masses and spins, detected the gravitational waves from their mergers, mapped their effects on surrounding matter. But we've never seen inside one. We never will. The event horizon is an absolute boundary, not just in space, but in information. What happens beyond it, at the singularity and the final moments of collapse, remains hidden, protected by the geometry of space-time itself. Some scientists speculate that black holes might be gateways to other universes, or to distant regions of our own universe connected by wormholes threading through higher dimensions. The mathematics allows for such structures, but there's no evidence they're real, and plenty of reasons to think they're not. Most likely, black holes are exactly what they seem, regions of space-time so warped that escape is impossible, containing singularities we don't fully understand, existing as reminders that the universe is stranger and deeper than our everyday experience suggests. And yet, for all their strangeness, black holes are natural. They're not anomalies or errors in the fabric of reality. They're the inevitable consequence of gravity, acting on massive objects of space-time, responding to the presence of mass and energy. They're predicted by the same equations that describe the gentle curve of Earth's orbit around the Sun, The same equations that let GPS satellites navigate the same equations that tell us how light bends when it passes near a massive object. Einstein's general relativity, for all its mathematical complexity, is a theory of profound simplicity. Mass curves space-time. Curved space-time guides motion. That's it. Everything else, the precession of Mercury's orbit, the bending of starlight, the slowing of time, the existence of black holes, all of it follows from that core idea. And black holes, in a sense, are the ultimate expression of that idea. They're places where curvature becomes so extreme that it dominates everything else, where the geometry of space-time folds in on itself, creating structures unlike anything else in the universe. We've come a long way in this journey, haven't we? We started with the simple observation that time slows near massive objects, that gravity affects not just space, but time itself. We explored how stars die, how some collapse into black holes, how the event horizon marks a point of no return. We talked about time dilation, about spaghettification, about the singularity hidden at the center. We listened to the gravitational waves from merging black holes, ripples in space-time itself, carrying news of the most violent events in the cosmos. And we've touched on the mysteries that remain, the questions we can't yet answer, the places where our theories break down. And we must admit we don't know. Black holes are in many ways the universe's way of telling us we're not done learning. They're puzzles, challenges, invitations to think deeper, to question, harder to push the boundaries of what we understand. And they're real, not just theoretical constructs, but actual objects out there in the night sky, shaping galaxies, bending light, warping time. When you look up at the stars tonight, remember that scattered among them, invisible but present, are places where time slows to a whisper, where light forgets how to escape, where the universe keeps its deepest secrets wrapped in darkness, hidden behind horizons we can never cross. And maybe that's okay. Maybe the universe is allowed to have mysteries. Maybe not everything needs to be understood, measured, explained. Maybe some things are beautiful precisely because they're strange, because they resist easy answers, because they force us to confront the limits of what we can know. But we try anyway, don't we? We build telescopes and detectors, we write equations and run simulations, we send probes into space and analyze data from distant galaxies. We're curious creatures always asking why, always reaching for the next horizon. And black holes, strange as they are, have rewarded that curiosity. They've taught us about gravity, about time, about the nature of reality itself. They've shown us that the universe is more flexible, more dynamic, more surprising than we ever imagined. There's a lesson in that, I think. Not just about physics, but about how we approach the unknown. Black holes were once considered absurd mathematical curiosities that couldn't possibly exist. Einstein himself doubted them. But observation proved them real. The universe doesn't care what we think is absurd or impossible. It follows its own rules, and our job is to discover what those rules are, to listen to what the universe is trying to tell us. And the universe, it turns out, has a lot to say. It speaks in gravitational waves in the light from distant quasars and the motion of stars orbiting invisible companions. It speaks in the mathematics of curved space-time, in the quantum fluctuations at event horizons, in the slow evaporation of black holes over time scales longer than imagination can hold. We're still learning how to listen, still building better instruments, developing better theories, asking better questions. And every answer we find opens up new mysteries, new puzzles, new frontiers. That's the nature of science. It's not about reaching a final destination, a point where everything is known and understood. It's about the journey, the process of discovery, the gradual accumulation of knowledge punctuated by moments of insight and revelation. Black holes, in that sense, are perfect symbols of the scientific endeavor. They're mysteries wrapped in darkness, surrounded by light we can measure and study. They're places where our understanding breaks down, but also places where we've learned more than we ever thought possible. So, rest now. Let these ideas settle drift. Find their place in your thoughts. You don't need to understand everything tonight. You don't need to hold all the numbers and equations in your mind. Just carry with you the wonder of it, the strangeness, the beauty of a universe that contains objects so extreme, so far beyond everyday experience, that they bend time itself. Somewhere out there right now, black holes are merging, sending gravitational waves across the cosmos. Stars are collapsing, forming new black holes adding to the population. Sagittarius A. At the center of our galaxy sits quietly anchoring the Milky Way patient and dark, and time that most familiar and mysterious of phenomena flows at different rates depending on where you are, how fast you're moving, how deeply you're embedded in a gravitational field. The universe is vast and strange and full of wonders. Black holes are just one chapter in its story, one piece of a puzzle that stretches from the smallest quantum fluctuations to the largest structures in the cosmos, from the first moments of the Big Bang to the distant future when the last stars fade and the last black holes evaporate into darkness. We're fortunate to live in a time when we can study these things, when we have the tools and the knowledge to peer into the deepest mysteries. Not so long ago, black holes were speculation. Now, they're science confirmed by observation, measured with precision. What will we discover next? What other secrets is the universe keeping? We don't know. And that's the most exciting part. Thank you for drifting with me through this quiet exploration of the places where time slows and light surrenders. Thank you for your curiosity, your patience, your willingness to sit with strange ideas and let them unfold. If you enjoyed this journey, there are more stories waiting, more mysteries to explore, more quiet nights to spend together, wandering through the wonders of the cosmos. Until then, sleep well, dream gently, and remember, somewhere in the darkness, between the stars, black holes are waiting patient and silent, keeping time in ways we're only beginning to understand. Good night,